Hello. You guys can hear me? Can anyone say it's okay? Am I already visible? Let me check my link. Why is my stream not working? Yeah, it seems to be decent. Okay, we should start soon. Hey guys, what's up? Hello Amog, hello Think, PCs and Alright, what's up Gaurav? Okay, give me a second. Can someone say if you guys can hear me? I'm still just want to check my audio a bit. Anybody? Yeah. Okay, good. So, okay, I guess I'll just get started now, I guess. Today we're going to talk about the IPFS, the permanent web, and generally we'll talk about the difference between a centralized and a decentralized protocol and how we go forward with it. So, to generally think, you can think of a centralized protocol like generally like HTTP or how you serve websites normally in the web these days from a server. And something decentralized could be something like your blockchain, the IPFS protocol itself, something called holochain, IOTA, and so forth. My name is Akilan Selvacoumar. I am the Heritage Tech Lab president. My website is akilan.io, and my email is akilan@hwtech.lab. So for this talk, all you need to understand is how the Linux file system works, just the fundamentals of it, the fundamentals of hashing and networks, how do routing tables work generally, as we're speaking. Okay, so what are the problems of the current web today? The current web is centralized. If you think of it, companies like AWS, Google Cloud have a large market share in the cloud space. AWS has around 40% market share, Google around 10%, and Azure around 20%. And the problem is most of our business applications are personal websites. All of them are hosted on these servers. And if these, let's say an entire warehouse fails, at a point of time in the future, you could see a third of the web disappear. And these guys have access to your personal data and they can do anything with it. And as you must have heard in the Congress sessions of how they exploit it, for example, when you're selling your ebook on Amazon, if you're a threat to them, they tend to try to remove your book off their website or purposely not let it feature in the front page just because you're a threat to them. And these companies love to be monopoly, and they do not like other companies to grow up beyond a specific limit. And this also comes in play with their servers. So the point of the internet is to be completely decentralized, where we all have our own machines and we host our own content from our own machines. And at the current status, this is not happening, not good, and big problem for us. The next problem is the current web is inefficient and expensive. When we push data on the web, there's a lot of duplicate content. We tend to pull files off. So we tend to pull files off a location which is much farther rather than choosing to pull from a location close by. It's, for example, going to McDonald's in the Dubai Mall instead of going to McDonald's close by to my house to buy a burger. And also, the current IPFS also has something called asynchronous downloads, where you can download multiple files simultaneously, which the current HTTP cannot do. And we'll talk about this further later. Let's talk about the IPFS stack. So IPFS stands for Interplanetary File System. We have something called the application layer. We have the naming layer, Merkle DAG, exchange, routing, and network. The application could be a game, it could be a chat app, it could be a website, anything, like a mobile app. Your naming is like a DNS entry, or we'll talk about this later, how we can use a single link to point to multiple versions of your website or the newest version of your website. IPLD is the data structure which IPFS uses, what we call the Merkle DAG. It's similar to Git. The exchanges, so currently we use HTTP. IPFS uses something called BitSwap for taking care of the exchanges of files. We have the routing layer, which is how to find out which node has that data or which node has the content, and the network, where an all can be on IPFS. So we can, for example, we can run IPFS on Bluetooth and other protocols. We'll talk about this in the coming slides. Okay, so this is the current way we get data. So to start with a simple analogy, to my previous example, let's say I want to get a Big Mac burger, and the current way I do it in the web is like I issue something like, take me to the Dubai Mall, I go to McDonald's, I get my Big Mac, I come back home, and then I eat my Big Mac. And let's say the time of this entire operation is around 2 hours because it takes 40 minutes back and forth from my house. And this is kind of inefficient. What if I just ask a simple question? Tell me where's the nearest McDonald's? And if I ask this question, maybe there's 1-2 minutes away from my house. I can go there, get my burger, come back home, eat it, and maybe the time of the entire operation would be under 40 minutes or something like that, which saves a lot of time. And this is the current issue we're facing. So to give an example here, this is what we do for location-based addressing. We have blogs.hwtech.club/post/flightsim2020, for example. So for blogs.hwtech.club, we go to the DNS server, check for an IP address. If there's an IP address, which is the domain name server, we get the IP address back. With the IP address, we request for content in the web server and get it back. And this is how we currently do calls on our website if we're loading any data. IPFS, rather, searches based on your data over here. So if I double click this link, you can see this entire website has been hashed to this unique value over here. So we'll talk about this a bit later, but generally we can search data by just using a huge hash. And so by doing this, we can pull data from the nearest node rather than going to some far off location. And let me talk to the next slide. So what is this hash? How do we derive it? So for example, we have a photo here. We convert it to binary. So we take this cat picture, we convert it to binary, and this binary is converted to something called SHA-256. So the reason we do this, and this is just basically a hashing algorithm for getting a unique value for your cat image. And it's kind of a security feature, because if you change 1 pixel in your cat image, the entire hash would change. And if you've done like your C coursework, you must have heard of something called Stegnography, where you try to add some malicious code inside your image to execute on another computer and so on. And if you do that in the IPFS network, or you try to tamper content in your image, it could change the complete hash, which means it's a completely new URL to the user, and probably they would not access it. And so this is technically how we get a hash and how we add the picture to the network. And we have this final abstraction called a CID, or called a content ID. So just let's assume that SHA-2 gets hacked or something. So someone finds a way to hide malicious content in the image and have the same hash ID. And this happened previously for SHA-1, and Google found a way to break it they took them a year, but they figured out a way to break it through. Let's say someone does the same for our encryption here, SHA-256. Now, so we know about this vulnerability. We need to we need to find a way to have a new hashing algorithm throughout the entire network, which is more secure. And that's what Content ID does. The first Q is a hexadecimal to a number in a table pointing to the type of encryption you're using. Probably the second character is the length of the hash itself. And using a simple table like this, we can have multiple hashing algorithms in the same network. So that this means we can kind of keep it to the latest hashing algorithm on the network itself. Okay, so our next part. So actually, there's something interesting in peer-to-peer networks. When you upload a file or anything, you actually chunk them into multiple bits. The reason you chunk is, one, you want to reduce duplicate content, and number two would be that if you actually chunk the files, it's actually faster to download. It's something to do by read and write in the file system itself. And so what we do in IPFS is we have a default chunk value, which is 256 kilobytes. This value can be, it does not have to be 256 kilobytes. It can be any value according to where you wish. For example, BitTorrent has a dynamic value, and they chunk based on the file size and the file type. And for example, in IPFS, we've chunked the cat's image into 3 chunks. We have the content IDs over here. What we do is we take these 2 IDs. So we use something called Merkle DAG, and I'll give like a simple explanation for now. So what we do in Merkle DAG is, let's take chunk 1 and chunk 2. We concatenate both of them, and then this entire hash is converted. So this entire concatenation, this huge string, is converted into this small hash value. And the same thing applies here. This concatenates with this hash. You get this huge string, you convert it to another hash, you just rehash it again. And by doing this, you get a base CID. So you can think of it like when you're having a website and you want to load the entire information in the folder. So you want to load the CSS files, the index of HTML files, everything you need. You would search using this base CID and so forth. So just think of it as a tree for now, and I'll try to explain what's the difference between a DAG and a tree. What you see on your left side is a tree, and what you see on your right side is the DAG. They're literally almost the same, but the only difference is a tree can have duplicate hashes, but a DAG cannot have duplicate hashes, and that's the only difference. The reason we don't call it a tree is because it becomes a graph at some times. So we can just call a DAG an acyclic graph, which makes more sense. Okay, our final point. We have something interesting in IPFS called IPNS, the Interplanetary Naming System. So as we learned before, if we change a content in the image or your website, we get a completely new hash value. To give a simple example, I have a McDonald's e-commerce website where I can order my burgers and they deliver it home to me. But let's say I change my website every week I change the content. So every week I get a new hash for the website. That means I get a completely new URL every week. And this could be problematic because how do we inform to the consumer that the URL has changed? The URL has changed and it's coming from an authentic person. It's coming from the actual McDonald's guy. It's not some hacker trying to fool you with something. So we use something called IPNS. What we do is in Linux, we have something called a public and a private key. So we generate our own public and private key. We take the public key, we get the hash value of the public key, and that public key points to the newest version of your website or your IPFS object, and that means that you can use the same hash and point and still view the newer version of the website, no matter how how much of content is changed in it. And this is like a cool security feature. And if you have like a DNS table, it makes your life easier. You don't have to every time go and change the entries on your DNS table. And any questions so far, or anything is confusing? I hope I was clear on what I said. Anything? So, okay, I guess I will continue with my demo. Oh, thanks, Manav. That's good here. Let me get started with my demo. Before I start, can anybody see my screen, or should I increase my font? I will just assume no one can see. I'll just increase my font. 23 will do. Right. Okay. So this is just a terminal over here. Linux terminal, normal stuff. I'm in the directory documents tech club, and first let's talk about how to add content, or how to add a website to IPFS. So first you have to check if you have IPFS installed. As you can see here, I already have IPFS installed, and it's a very easy command. It's just IPFS, and you have your CLI over here with multiple commands, and there's a lot of things you can do with it. But let's just get started to adding content. So let me see what files I have here. I want to add the IOE underscore website. Just TLS heavy IOE underscore website. Okay, as you can see here, I have a simple website over here, a simple static website, and let me show you how we can add it to the network. So it's actually super easy. IPFS, add recursively IOE, the folder we want to add. And as you can see here, we have actually added the website to the network. And to actually start the network, all we have to do is run a command called IPFS daemon, and this starts the network. So this means now I'm connecting to other nodes in the network, so that we can actually so that we can write as a peer-to-peer protocol. So what we do is copy this hash value itself. To prove it to you that it's on the network, I will go here. We'll give an increase in font. I hope my localhost 8080/IPFS, and what I'm going to do here is my local node itself paste this hash over here. So I paste the hash. So in my local network, this proves that the website is on the network, and I can access it from locally on my computer. And I can show you the IPFS. This is the IPFS admin UI. We have something called a peer ID over here, which is a unique value of your node in the network. You can see that I have discovered 814 peers. And when you add a file in IP address, when you do IPFS add, by default, it pins all the files over here. So you can see all the files I've added in my network. Now, to prove it to you it's in my network, let me show you how I can pull the file from another computer. So for that, I will go here, I will switch it to the other computer. Transition, and from here, let me open the terminal up. So this is a completely different node. Can do is, let me try to increase the font over here also. Preferences, text, should have done this before, but no worries. Why are you being strange, computer? Okay, I can't do much about it. I have to apologize, but have to bear with me with this font. Or Control ++. Why is not showing text type? Okay, either way, it's just basic commands. First, we do IPFS init to just start the, IPFS daemon to just start the network through. Just give it a while. So we have it here. As you can see, I've started this network on my secondary computer. All I do is go here, localhost 8080/IPFS / is this hash? No, sorry, wrong website. I pulled the wrong website, my bad. /IPFS. All I need to do is actually find a way to run this entire hash on my other computer, ZE. FSQM. Okay, actually already have this, thank God. As you can see, I have officially opened this from another computer. I just had to search the hash and it automatically fetched the file. And to prove it to you that it's actually there on the network, I can do one more thing. So I can go here, I can do IPFS. I can open it from a remote gateway. Let me see if I can post it on the chat for you guys to see the entire thing. QM Z. Let me find a way to copy the hash. Okay, this is on the network and I will send you the link over here so you guys can see exactly the website I've deployed on the network, and to prove to you that I've pulled it from a closest node, or from my closest node, I will open the web UI on another this tab over here. We'll increase the font size so that you guys can. My computer's being slow today. Okay, so if I show you my peers, can I check? Actually, oh, that's strange. It's not even covered my peer, but generally, when you're testing this on the top, you'd have your local host connection. It takes a while sometimes, but I mean, because in my case this time it actually pulled from another IPFS server because it hasn't discovered my other computer, but generally it pulled it from the local network as I tested further. So, but yeah, at least it works on the network and it's running. We have a website running distributed, so yeah, it's pretty impressive for me. Let's go back to the slides. Transition back. Are there any questions till now? Let me check. Any questions, or have I been clear? Anything I've not said clear enough? Anything? Okay, I will proceed forward, I guess. Okay, no questions. Okay, now let's talk about something in IPFS we have called bitswap. So let's say so now the next question is like, I have the hash, how do I get the content from the network itself? So all I do is we have a simple protocol called bitswap. I take the hash. First I ask all my possible neighbors, do you have this hash, or do you have the content for this hash in your network? Do you have the content for this hash in your network? And I keep asking every single possible neighbor first, and let's say they have a mixed answer, yes, no, yes, no, yes, no, yes, no, yes, no. All I do in this case is I check the node that probably says for yes first, and I pull it from, once he says yes, I pull it from that node, and then I've got the file. But if, let's say for example, all my nodes say no, and none of my neighbors have it, then what I do is actually I do something called querying the DHT table. That means I try to do a few hops to check and see if other nodes have that hash which I'm searching for. And let's talk about a bit more about DHT. So DHT, we use something called a distributed hash table in IPFS. So a DHT is just like your hash map, but think of it in the terms of a routing table. When you have So generally in the net, we use something called a routing table. So let's say you're searching for an IP address or something. It should tell which node has that IP address and the website files in it, something like that. So in the terms of peer-to-peer network, what you technically have to do is store the route information for all the nodes in the network. And this, so a simple example could be the hash mapping to an IP address or something. And we have to store all of them if you want to, technically speaking, fetch some sort of file in the network. And this could be huge. If we have like 10 million nodes, I don't think our computers would have the space to store all the routing table information. So all we do in mostly peer-to-peer networks is we take our hash map and we distribute it among the nodes. All our nodes have our own routing table, and we only store a little bit of the network. We don't store the entire routing information, just a small chunk of it, maybe of the peers we recently pulled or the neighbors we talked to, simple information like that. And doing that, our tables become much smaller, and in a way, it fixes the problem of it fixes the problem, and we can have as many nodes as possible, even 40 million, 50 million nodes, and still we would have a relatively small routing table. And we'll talk about in the next slide of an impressive algorithm of how even having such a small routing table, you can get information in like a few hops. So we have something called the Kademlia DHT, or Kademlia distributed hash table. This is just a simple routing algorithm. If we have 10 million nodes, we can always get a match if it's in the network within 20 hops. It has an order of log 2n. And it also has some interesting features. So let me try to tell you something about a problem we have in the we have in peer-to-peer networks. Generally, the big problem is like nodes keep coming online and offline pretty frequently, and this means the routing table could have a bunch of misinformation. Or when you're searching for a node, you take the following route, and then you find out the node's offline, and sometimes you cannot even load a page just because of this. And Kademlia DHT kind of tries to solve that problem by asynchronously sending queries like in multiple directions and seeing whoever gets a response first. And there's also like another problem. People try to do attacks in peer-to-peer networks by having like as many nodes as possible online and offline just suddenly. This means that you're misdirecting so many nodes and you can break the network in a way. So what Kademlia DHT does is it has like a metric. It tends to pull information or pull your website files from a node that's been longer time in the network, as the probability of it going offline is lesser. So this is something impressive Kademlia DHT does. You can check out their academic paper if you want to know more about them, but I mean, we can't cover much about it because it's just extremely complicated and it'll take me more than an hour to explain its workings. Okay, let's again come a recap of our Ipfs stack. We have something called the application. We have the naming, Merkle-DAG, exchange, routing. Application, as I told you, website, anything. Naming, think of it like a DNS entry, or you can have a single hash, no matter how much of content changes in your website or application. Merkle-DAG works exactly like Git. It's actually kind of Ipfs took the Git code base and did some modifications. Your exchange bitswap is the same thing BitTorrent uses, but just Ipfs you can do asynchronous downloads in Ipfs. Your routing, you can think of it as a distributed hash table. And now comes an interesting feature. Ipfs can work completely offline. You can build an offline messaging app, and when you have calamities, you can connect each of your phones using Bluetooth to each other. And if you run Ipfs as top of it, because remember, Ipfs is not a protocol, it's an overlay. So it's an overlay that creates efficiencies in searching. So when you run Ipfs as your overlay on top of your Bluetooth network, you can have an offline chat app. You can have your own routing tables within each of your phones. So all your phones or all your devices on the Bluetooth network act as a router or something of that sort. And this can be very, very useful. And yeah, that's like the biggest advantage of running an Ipfs overlay. It's very flexible and it's also very resilient if you think of it. Okay, let's talk about some stuff, some developments in Ipfs. The Ipfs developers have made something called Filecoin. So So with Filecoin, basically you can store IPFS objects of other users, and in the future, if you have a huge company, you can store company data and get paid by a cryptocurrency called Filecoin mining. Filecoin, and this helps create a decentralized economy and gives you one revenue stream. So time to use those hard drives which you've never used before. And you can read more about Filecoin on the website, filecoin.io, to check more about them. You can also build games in IPFS using their Unity library. So you can each game you can break a game into smaller chunks, and then each chunk has into smaller chunks. And then, so for example, if your game is popular, it will load each map from a different computer, and you can check out their link over here. I will update the description later. And actually, Minecraft. Some people have tried to make Minecraft maps in IPFS, so you can have a Minecraft map that you can load decentrally from your nearest peer instead of a centralized server. That's another interesting development. Companies like Netflix use IPFS internally. So Netflix has around like 500 Docker containers in a day. So rather than pulling the Docker container from like a centralized server or centralized repository, they can use IPFS to run it as their own CDNs. So they pull it from that nearest node, and IPFS is a very effective way as running as a CDN or content delivery network. And Netflix has configured it in a way that instead of pulling the entire container, they only pull the binary files out of it. That means they pull lesser data, and Netflix has been a huge contributor to IPFS BitSwap and sort. We have something called OrbitDB. It's a database which can run on IPFS itself. So you have data, if you put content in it, it's completely distributed among the nodes in the network. So yeah, it's possible to actually have a database in a distributed network. Who knew? Yay, blockchain, time to kick you out of the network. No more blockchain. Okay, what has TechLab been doing with IPFS? We have actually we in the backend team, we've been building our own static website generator or custom static generator, where you can type information on WhatsApp, and then you click deploy website, and it creates your own e-commerce website, which you created completely from WhatsApp. What you can do is we have another command where you can deploy that static web page on the IPFS network, or deploy your e-commerce website on a distributed network, making your e-commerce website run completely on the IPFS network. So you can technically say your application is kind of serverless. And these are the tools, these are the companies and tools that use IPFS. I think IPFS will become really popular when they're natively available in browsers. But at the moment, it's not natively available. You have to download it separately and run it on your computer as we're speaking. They have a companion, but it's easier to download it separately and run it. And what else we do have? So yeah, apart from that, and in IPFS, in a peer-to-peer network, generally the concept is every single node is a client and a server. So if you want to think of IPFS, think of it like every node is a client and server serving their own files. And I guess that's it. That's it for my talk. Do we have any questions for now? I hope I was clear, and I hope you guys understood what I said. When is TechLab shifting to IPFS? We will be doing soon. We just need to set up our own gateway so that we can keep the node up. If we get our VPS set up, and I can set like a stable gateway very soon. It would take at least 10 minutes max to set it up. Wouldn't take time at all. It's very easy to configure. Yeah, so I mean, because not many people run the IPFS network, we need to have a custom gateway. It's not possible to just deploy in the network and hope it's there. Yes, we need a VPS. We all want one. We just have to fight together. Are there any other questions? No. Yeah, hashtag to all budget. Yes. Any other questions apart from that? Okay, no questions. I will thank you guys for coming, and I shall end the stream for now. Thank you guys. Bye-bye.